Because it's really tempting right now to make 2 confidence intervals based on that data. But we don't want to do that, because if we make 2 confidence intervals, we lose our confidence, right? We lose our confidence. We can raise confidence to get back, but then we've already discussed what happens with that. If we raise confidence, we increase the chance of that type 2 error. So we don't want to do that. We want to be able to collapse this down to one curve. So let's think about this. Di, you've already got us part of the way, because she's already identified the variable we have to test. The variable we have to test is mu. Which distribution are we going to use for averages? Very nice. T. We need to use a T distribution. So what I'm going to do is, I'm going to put an old friend up here in the corner. Old friend. For one average. The test statistic we had to calculate looked like this. We only did it one time. You've been using the TI to do this since that one time. But the test statistic we used was a T, and it was formed by finding the difference between the average of our sample and the assumed average of our population, divided by the central limit theoremized standard deviation. That's what we did. We did it one time, we never did it again. But I want to refer back to it right now, because now we have to switch gears a little bit and know how to deal with this data over here. We've got to deal with this data over here. Can we adapt this for 2 averages? Can we adapt this for 2 averages? What do you think? In other words, can we get one T where we look at both things simultaneously? What do you think? Veronica said, vote for yes?
Yeah.
Go ahead, tell me how.
Could we square it?
Oh, and then do what with it? If we square it, I lose the units, don't I? I get square feet. When you say it, what do you mean, square it?
I don't know this formula.
Oh, I see. But that would be T squared, which is interesting to me. That does make me think what that would look like. Would it be 3-dimensional then? Huh. Let's not change the dimension. I want it to be just T, not T squared. I love that idea though. And we do have to do something with squaring at some point, I think. But let's try to keep it T. Well, let me ask you another question. X bar was the sample average, correct? How many sample averages do we now have?
2.
We have 2. What are we trying to see about those sample averages? You already done it for us, Danielle. You already did it for us when I asked you to report back on our sample averages over there. What did you say?
I said that on average it's 7.
How'd you do that? Don't overthink it.
I subtracted.
You subtracted them! To see if there was a difference, yes? If there were no difference, what would the subtraction yield? 0. Oh, 0. If there were no differences in the averages, the difference would be 0. But your difference was 7. My question, of course, is going to be what? 7's over here, yes? What's my question going to be, of course? How far over there? What we need to do is to take Danielle's idea of her difference in the averages and apply it to this curve. But we've got to know where 7 lies. Does 7 lie here? Does 7 lie here? Does 7 lie here? Does 7 lie over here? Because the further out it gets, the more significant the result, yes? And we have our measurement. So I think we need to start. We need to start with your calculation, Danielle. Instead of just x bar, let's start with x bar 1 minus x bar 2. Which will be 1 difference. Now some of you might be thinking, wait a minute, Rule, damn it, you just said we can't treat this like last week, which was the decibel differences in the commercial, and it was also the differences in your thumb and forefinger. My response is we're not treating it like last week. Last week, we did the differences and then took the average. Now, we're taking the averages and then doing the difference. See the difference in order? There's a change in the order. Yet last week, before we took an average, we subtracted your thumb minus your finger, or the commercial minus the TV show, or whatever minus whatever. Now, we're actually doing the averages first, independently, and then subtracting independent averages. This deals with that 21 versus 20 problem, doesn't it? Because you can take an independent average in a different sample size and then subtract the end results. Good. I'm not going to forget about those numbers. I think they're going to be important to us. Good. Excellent. So this, if you think about correspondences, what we just did right there, Danielle's given us a huge piece of the puzzle. She has given us the part of the test statistic that corresponds to this piece right here. Thank you. Wrong mistake. What's going to go here? Does it have to be? Keeping with Danielle's theory, this is our sample difference, but that's only useful if you're only going to stop talking at your sample. If I want to compare it to the population, I want to see if that difference holds up when scrutinized against the average, which would of course have to be, thank you Veronica, mu1 minus mu2. I'm going to put it in parentheses too because it's a subtraction across a difference. So that, right there, is going to have to be that. Just so you know, FYI, the lion's share of the time, the numerical value of the, that's dead. The numerical value of that difference in average is going to be 0. Most of the time. Most of the time it's going to be 0. Because you're trying to see if it's changed from what it was. Cantilevers, status quo, we're trying to see if V-brakes do a better job. If they don't, essentially it's 0. So most of the time, this whole quantity isn't even indicated. But I wanted to make sure you see the correspondence between where we are. Fair enough? Okay, fantastic. So all that does, Danielle, we now basically have a number we can plug into that. 7. 7. That Danielle gave us the value of this. It's 7. It's x bar 1, 23 minus 16.4, 6.6 feet, 6.5 feet. So now we know the top. But the top is never the problem in 244. The top is never the problem. What's the problem? I shouldn't say the problem. What's the discussion that needs to be had? What goes here? What do you think? What goes down here? What goes down there?
S1 minus S2 divided by square root of S1
Okay, so we have some votes. I love this. This is something I agonized with when I was first learning statistics. Now, as I told you guys often, when I first learned statistics, we were just given formulas and told to plug numbers into them. So what I had to do was write them down, memorize them, regurgitate them, and then weeks later process what the hell was going on. So we got a vote. One vote would be, say it again.
S1 minus S2 over the square root of N1 minus N2.
I have no problem with that whatsoever. Except for one, numerical one. It doesn't matter here. But what if your sample sizes are the same? Exactly the same. What happens then?
You get 0 and square root of 0.
You get something over 0, which mathematically is bad news, isn't it?
Yeah.
Shoot. So I don't think we can do N1 minus N2, because if we ever do have equal sample sizes, that's going to create an impossible mathematical situation. I love the idea, though.
Do we do the average?
Can we tell me how? Tell me how.
The average of the sample.
Oh, the average of the sample sizes. So in other words, instead of doing that, do the same thing, S1 minus S2 over maybe the square root of the average. I like that idea. Except I shouldn't do that. I should do a weighted average, probably. This is assuming the sample sizes are the same, so I have to do a weighted average instead of that. I like that. I like that very much. I like that very much. Any other ideas? I think the result is wickedly surprising and not what you're expecting at all. However, we're at 9 o'clock. Let's take 5, go get some air. You're going to want air to this next bit. Seriously. I worked for years to explain this the best possible way. I think I finally got a demonstration that explains it. It's counterintuitive. It's counterintuitive. We'll come back. We'll come back.